This is Eric Michael Lloyd. I have a master's in psychology, neuropsychology concentration. I wanted to read an article by Plus One. This article was published in 2019, in August of that year. This one is on a more grim subject. The subject heading or the title is "What Have We Learned from the Time Trend of Mass Shootings in the U.S.?" The authors are Ping I. Lin, Lin Fei, Drew Barsman, and M. Hussain. This was published October 18th, 2018. Abstract. Little is known regarding the time trend of mass shootings and associated risk factors. In the current study, we intended to explore the time trend and relevant risk factors for mass shootings in the U.S. We attempted to identify factors associated with incidence rates of mass shootings at the population level. We evaluated if state-level gun ownership rate, serious mental illness rate, poverty percentage, and gun law permissiveness could predict the state-level mass shooting rate using the Bayesian zero-inflated Poisson regression model. We also tested if the nationwide incidence rate of mass shootings increased over the past 3 decades using the non-homogeneous Poisson regression model. We further examined if the frequency of online media coverage and online search interest levels correlated with the interval between 2 consecutive incidents. The results suggest an increasing trend of mass shooting incidences over time. P-value is greater than 99%. P is less than 0.001. However, none of the state-level variables could predict the mass shooting rate. Interestingly, we have found inverse correlations between the interval between consecutive shootings and the frequency of online-related reports, as well as online search interests, respectively. P-value less than 0.001. Therefore, our findings suggest that online media might correlate with the increasing incidence rates of mass shootings. Future research is warranted to continue monitoring if the incidence rates of mass shootings change with any population level factors in order to inform us of possible prevention strategies. This article was received August 14, 2017. It was accepted in August 28th of that month, 2018, and was published in October, the 18th day in 2018. This article has a copyright 2018 Lin et al. It's an open access article distributed under the terms of Creative Commons Attribution License, which permits unrestricted use, distribution, and reproduction in any medium, provided the original author and source are cited. There's no competing interests. They declare that no competing interest exists. The funding, the authors receive no specific funding for this work. The editor is Natalia L. Komarova, University of California, Irvine, United States. Introduction. Although mass shootings are rare, violent behaviors compared with other violent crimes, these incidents adversely impact society as a whole. A better understanding of risk factors associated with such violent behaviors could provide an initial key to possible intervention strategies. There have been only a handful of published studies that identified risk factors for mass shootings. The limited published findings may be, at least in part, attributable to their rarity that strains the analytic techniques. To partially circumvent this technical challenge, one may explore risk factors at the population level, which may shed some light on points of prevention from the perspective of public health. Therefore, we attempted to identify several population-level risk factors associated with such incidents in the current study. The literature suggests several risk factors associated with homicides, which may provide some clues to possible risk factors for mass shootings. Accumulating evidence suggests that gun ownership is associated with gun-related deaths. Although firearm-related murder rates are related to area-based gun ownership rate, it remains unclear whether incidences of mass shootings are attributable to the gun ownership rate. Emergent, albeit inconsistent, evidence has also indicated that mental health may play a role in mass murders. Poverty has been documented to be associated with the homicide rate, but to our knowledge, its link with mass shootings has not been evaluated yet. Another population-level risk factor associated with mass murders is the contagion effect, which refers to the phenomenon a murderer may temporarily increase the probability of a similar event in the proximal future. Contagion effect. So the phenomenon a murder may temporarily increase the probability of a similar event in the proximal future. It remains unclear if such a contagious effect is triggered by increased attention, which may be reflected by the quality of media coverage of the key event in the community. Media exposure of mass violent incidences has been found to adversely impact mental health of children and adolescents. A Finnish study reports that media exposure was positively associated with the post-traumatic stress symptoms following a school shooting event. Research prior to 1990 has shown that behaviors and value systems are shaped by media to some degree. However, the link between media exposure to violent behaviors in children and adolescents remains controversial. Heterogeneous research methods may have caused inconsistent findings. There has been scarce published research about the impact of media exposure on mass shooting incidents. Furthermore, little is known about whether media coverage on such incidents may contribute to the time trend of such extreme violence. The limited understanding of mass shootings may have hindered the progress in dealing with this rising threat to public health. We propose to address three major questions in this study as follows. What are the population-level factors associated with the probability of mass shootings? Is the incidence rate of mass shootings increasing during the past 3 decades? Incidence rate of mass shootings are they increasing in the past 3 decades? Is the online media associated with probable contagious effect online? We believe the answers to these three major questions will clarify some population-level risk factors for mass shootings and provide some clues to how the public policies should react to this problem if these risk factors are modifiable. For example, poverty rate. In the current study, we have gathered relevant information about mass shootings that occurred within the U.S. in the past 30 years to assess whether there are any systematic temporal and spatial patterns, and to examine whether these incidences can be explained by risk factors. Methods. Data source. The definition of such an event is critical in the research on mass shootings. The definition of mass shooting is particularly critical in the current study since the rates of such an event is the key outcome. In our analysis, we defined a mass shooting as an act of firearm violence that resulted in at least 4 fatalities, not including the perpetrator. One at the same time or a relatively short period of time in the case of shooting sprees. This definition is partially based on the definition of mass murder from a report of FBI Behavioral Analysis Unit. Additionally, we attempted to focus on mass shootings unlike conventional homicidal behaviors. As stated in A Guide to Mass Shootings in America, the editors of Mother Jones website wrote, "Our research has focused on indiscriminate rampages in public places resulting in 4 or more victims killed by the attacker. We exclude shootings stemming from more conventional crimes such as armed robbery or gang violence. We therefore choose Mother Jones' website as the main source of our data, where 100 mass shootings were selected from January 1982 to May of 2018. The data related to the state-level gun ownership rate were estimated from the proportion of firearm-related suicides and all suicides acquired from the WIS-QARS database associated with the Center for Disease Control. We first selected suicide in the section entitled Intent or Manner of the Injury, and then selected firearm versus non-firearm in the selection entitled Cause or Mechanism of the Injury to extract the state-specific numbers of firearm-related suicides and non-firearm-related suicides from 2013 through 2016, respectively. The gun ownership was then calculated as the average number of firearm-related suicides divided by the average number of all suicides during this period of time. The data of state-level serious mental illness rates were extracted from the CDC report, Mental Illness Survey Among U.S. Adults, which included the state-specific rate of serious psychological distress among adults aged greater than or equal to 18 years. Briefly, we used the online tool Behavioral Risk Factor Surveillance System to select the lifetime depression prevalence rate by state as a proxy for the state-specific mental illness rate. We further retrieved the data of poverty rates by state from the United States Census Bureau by selecting the income and poverty table by each state during 2013 through 2016 on QuickFacts webpage. A number of online reports about mass shootings were extracted using Google search engine. We used the Allentext function in the Google search engine, and then specified the time frame using the function of research tools to calculate the number of online posted articles between 2 consecutive incidents. Briefly, we have used the following keywords: mass shootings, or rampage shootings, to extract all online public reports and posts that discuss mass shooting following a specific mass shooting event. The media coverage density, daily number of online reports and posts, was then calculated as the number of online articles divided by the length of period between the relevant incident and the next incident. Previous studies have shown that the Google searching engine can effectively retrieve the information about the impact of the media. We also compiled the data of interest search interests, which was derived from Google Trends database. We extracted the data related to interest levels of internet searching using keyword mass shooting or rampage shooting in the U.S. during 2005 through 2017. Search interest was defined as the relative percentage of searches compared to the peak in the specified time period. We chose to focus on the data after January 1st, 2004, since Google Trends started to store the data of users' internet search histories in late 2004. The detailed raw data are stored in a cross-disciplinary repository, Figshare. Statistical methods. To investigate the impact of state-level gun ownership rate on the mass shooting rate, we built a Poisson model for state-specific incidence count with other covariate effects such as state-specific serious mental illness rate and poverty percentage, and population size as an offset variable in a Bayesian framework, with two random effects for structured and unstructured spatial correlation structure. Since there were no mass shooting incidents in 19 states during this period of 32 years, we used zero-inflated Poisson count model to adjust for the excessive zeros. All incidents were summarized by state as counts regressed on gun ownership rate through a log link function as log mean count for state I equals log population I plus beta 1 plus beta 2 times gun ownership rate I plus beta 3 serious mental illness rate I plus beta 4 poverty times poverty percentage I plus VI V subscript I and plus U subscript L, where VI is structured random state effect with an intrinsic conditional autoregressive CAR model was specified as a prior distribution, and U subscript I is unstructured random effect with an exchangeable normal distribution with zero mean as a prior distribution. The use of spatial model, specifically the CAR model, was intended to adjust for the effect or similar neighborhood characteristics among the states sharing common borders. The model can examine not only the state's mass shooting rate, but also the corresponding rates in all surrounding states. Therefore, spatial modeling could enhance both the estimates of our knowledge of the degree of uncertainty associated with these estimates, and may overcome the effect of artificial state boundaries. The model for the excess zeros considers the same predictors as the main Poisson model. In addition, we also treated the logarithms of state-specific population size as an offset instead of a covariate to examine the relationship between covariance and probability of shooting. To evaluate if the incidence rate was increasing during the past 3 decades, we implemented a non-homogeneous Poisson regression model on biannual incidence count for the U.S. with a linear year predictor to characterize the time trend. A quadratic term turns out to be non-significant. Formally, the Poisson regression model is nationwide count from 2 minus year time period I is equal to beta 1 plus beta 2 times years since 1982. We also analyzed the annual count of mass shootings using a similar model for comparison of effects and models goodness of fit based on Akaike Information Criteria, AIC. We also assessed if inter-incidence time intervals in days decreased in recent years. Assuming the time intervals follow a time-dependent exponential distribution, we would be able to predict the risk of future incidences based on the incidence rate in the preceding 2-year period. We further investigated the speculated relationship between mass shootings and 2 online media indices, online media coverage and online search interest. We hypothesized that the higher online media coverage density, meaning the frequency of online media attention to the theme of mass shootings in a certain period of time after a particular shooting, might be associated with the shorter interval between this incident and the next one. We therefore calculated the online media coverage density by calculating the daily number of reports and posts about mass shootings during the interval between two consecutive incidents to investigate if media attention between an earlier shooting event could correlate when the next shooting might occur. To alleviate the confounding effect due to the time trend that Google became the dominating internet searching service provider in late 2004, we only analyzed a subset of mass shooting incidences in our data set that occurred between January 2005 and May of 2018. The distributions of media coverage density were highly skewed. Hence, we log transformed the variable of media coverage density before we performed the Poisson regression model to see if the between incident interval could be predicted by media coverage density adjusting for the number of fatalities and number of injuries with time as an offset. Similarly, we tested if the outcome could be predicted by the level of internet search interest. Finally, we evaluated the associations between the outcome and both online media coverage density and search interest levels by adjusting the numbers of fatalities and injuries in the same Poisson model. Results. There was a total of 100 mass shootings in the U.S. recorded in our compilation data from January 1982 to May 2018, with 833 fatalities and 1,292 injuries. The spatial locations of the shootings in the 48 states are displayed in Figure 1. Table 1 displays the results from the fitted Bayesian zero-inflated Poisson regression model, which show that no state-level variables were statistically significantly associated with the number of mass shootings in each state. The goodness of fit value based on deviance information criteria, aka DIC, of a zero-inflated Poisson regression model was 102.5 compared with the Poisson regression model of which the DIC value was 145.7. Therefore, the Bayesian zero-inflated Poisson regression model still had a better model fit than the Bayesian Poisson regression model. The two Poisson regression models that examine the incident rate show that the frequency of mass shootings has been increasing in recent 3 decades. The p-value is less than 0.001. According to the AIC level, the model that focused on the biannual incidence rate may have a better goodness of fit than the model focusing on the annual incidence rate. AIC levels were 93 and 122 respectively. The biannual incidence rates are shown in S1 figure. The frequency can be reflected by the time interval between two consecutive incidents, also known as inter-arrival time in a Poisson process. We plotted inter-arrival times, figure 2, using a GAM fit, generalized additive model with smoothing spline of 4 degrees of freedom to illustrate the time trend of incidence rates. If the trend is not present, meaning the Poisson process is homogeneous, the inter-arrival time would follow a fixed exponential distribution with an intensity parameter lambda. We estimated this parameter by a maximum likelihood estimate and converted it to a monthly rate. Lambda subscript m is equal to 0.227. This value could inform us of the risk for future mass shootings in the U.S. To model the temporary trend for incidence rates, we adjusted the model with a time-varying Poisson process. For example, meaning a non-constant rate lambda for the exponential distributions of inter-arrival time. In this model, The counts from every 2 years were calculated. The log lambda t, the logarithm of 2-year expected count, was treated as a linear function of time. The resulting regression model was as follows. Log lambda t is equal to 0.55683 plus 0.05033 times the year minus 1982, the years since 1982. The regression coefficient was highly significant. The p-value was less than 0.001, but the quadratic term in the model was not significant. A fitted regression line superimposed on the distribution is shown in S2 figure. According to the Poisson model, the possible over-dispersion parameter was estimated to be 1.53, which indicates a moderate effect. If the current frequency trends continue, we can assess the risk by adopting the monthly intensity rate from the above non-homogeneous Poisson model for the most recent year, lambda subscript m 0.468. See third column of Table 2. Table 2 shows the predicted probability of at least one mass shooting within the next few months, as the DOI as well, in the link. In an attempt to explain this time trend, we performed a pairwise correlation analysis of online media coverage, online search interest levels, and mass shootings. The correlation analysis results are summarized in S1 table. It shows that both media coverage and search interests were inversely associated with the interval Spearman's correlation coefficient. P is equal to negative 0.7, P is lesser than 0.001. Figure 3 shows the local polynomial smooth line that indicates the relationship between the online media indices, for example, the number of public reports and posts per day, and search interests, respectively, and the interval between the two consecutive incidences. The two indexes were both inversely correlated with the time interval between two consecutive incidents. We further found that the temporal order, the calendar time since 1982 in our case, was also inversely associated with the interval. P-value is negative 0.37, p-value is equal to 0.001. Because of the significant correlation between media coverage and temporal order, we used a ridge regression of inter-arrival interval on media coverage and time. Media coverage remained significantly correlated with between incident interval after controlling for temporal order based on the ridge regression model. Coefficient is negative 0.147, p-value is 0.006. Since internet search level was highly correlated with media coverage, the final fitted model selected media coverage over internet search interest levels. Discussion. Figure 3 shows the relationship between online media coverage density, for example, the number of public posts and reports per day, panel A, and online search interest, panel B, for the preceding shooting incident, and the interval between two consecutive shooting incidents is illustrated. The trend is presented as a polynomial smooth line with 95% confidence interval superimposed on the scatter plot, as the link is there as well. I'll put a link to the article as well within the video. Discussion. Our study has attempted to answer 3 important questions concerning population level risk factors associated with mass shootings, increasing rate of mass shooting, and the contagious effect. The results suggest that neither proportion of suicides by firearms as a proxy for gun ownership, poverty rate, nor serious mental illness rate could significantly predict the state-specific mass shooting rate. However, both annual and biannual incident rates of mass shootings in the U.S. have been found to steadily increase during the past 30 years. We further observed that the increasing online media attention is correlated with decreasing intervals between shooting incidents, which might consider to lend some support to the hypothesis of a contagious effect. Both gun ownership and the rate of mass shootings declined simultaneously in Australia during 1979 through 2013. Our study did not obtain similar findings related to gun ownership, which might be partly attributable to our use of a different measurement to calculate the proxy for gun ownership due to the limited data on gun ownership in the US. Notably, the Australia study had a stricter definition of mass shooting. At least 5 victims were murdered, for example. The relationship between the gun ownership and mass shooting rate might be confounded by gun law permissiveness, since gun law permissiveness was found to influence the homicide rate. We hence propose that alternative hypothesis that gun law permissiveness may influence either gun ownership or shooting rate, so it could be considered as a confounder. There are only 9 states where law enforcement officials could exert wide discretion over whether to issue concealed carry permits. These states are California, Connecticut, Delaware, Hawaii, Maryland, Massachusetts, New Jersey, New York, and Rhode Island. This statement was based on individual state laws, which include California Penal Code, Statute 26150 and Statute 26155, Connecticut General Statutes 29 through 28, Delaware Statutes 1441, Hawaii Revised Statutes 134 through 9 through 139, Maryland Public Safety Code, Statute 5 through 306, Massachusetts General Laws, Statute 140, 131, and 131, New Jersey Statutes 2C 58 through 4, 58-4, and General Laws of Rhode Island, Statute 11-47-11. The results, based on Bayesian zero-inflated Poisson regression model, show that gun law permissiveness was only nominally correlated with gun ownership. Kendall correlation test p-value 0.06, and gun ownership was not statistically associated with the mass shooting rate, with or without gun law permissiveness being adjusted in the statistical model. Our data suggests that the state level rate of serious mental illness could not predict the mass shooting rate. There is evidence for an increased prevalence and severity of mental illness in adults in recent years. For example, from 1991 through 1992 to 2001 through 2002, the U.S. adult prevalence for major depression significantly increased from 3.33% to 7.06%. However, such studies are difficult to interpret because the increased prevalence may be related to increased help-seeking behavior, better screening, or other confounding factors. The link between mental disorders and mass shooting may be one of the problematic self-evident assumptions which tend to oversimplify the causes of such violent behaviors. Future research is needed to investigate any correlations between the increased frequency of mass shootings, types of mental illness, psychiatric medication non-adherence, and increased need for more psychiatric services. Our results suggest that the online media coverage of current shootings as well as internet search interest levels may predict how soon the next shooting tragedy may occur. The positive correlation between online media coverage and search interest might provide some clues for the predisposing factors underlying the contagion effect. However, our estimates based on population level data may not reflect the genuine influence of media exposure on individuals. With the growing popularity of social networking online media, the media exposure to mass shootings solely based on internet-based reports may underestimate the total level of relevant media exposure, since most of the social networking media related activities cannot be directly accessed through online data queries. Although we cannot rule out some of the confounders for the relationship between media coverage and the rising incidence of mass shootings, media exposure seems to play a role. There have been several recent studies using Google to study social behaviors. 3 have been focused on violent behaviors. Therefore, the high-efficiency internet search engine has the reliable capacity of capturing interest level associated with violence in at least internet users. Our media-related analysis has several limitations. First, we only focused on the most proximal preceding incident, and hence we ignored the impact of media coverage on more distant incidents. Although the media coverage on cumulative mass shooting incidents is overall greater at more recent time points compared to earlier incidents, we could not rule out the confounding effect of some incidents that generated more media attention despite being temporarily more distant. The confounding effect, if present, would by default make recent incidents subject to higher levels of accumulative influence of media. We have adjusted for the temporal order and found the effect of media coverage remained significant. Meanwhile, we also examined the role of online search interest levels in the incidence of mass shootings. Online search interest did positively correlate with online media coverage. Therefore, we might infer the frequency of online-related reports might reflect both interest levels of the media providers and consumers and vice versa. Second, we calculated the media coverage by counting the number of online reports. However, the emergence of social networking web resources may play a role in the time-dependent increment of media exposure to these incidents. Such a confounding effect of social networking could not be measured with the current analytic methods. Similarly, the internet search interest levels could not capture the interest levels of consumers in the social media. Although online news reports and articles only represent a fraction of media exposure related to mass shootings, online articles, especially those related to social networking, for example Twitter, may correlate with other types of media coverage such as television. Therefore, online news reports may serve as a proxy for media exposure to a particular mass shooting incident. Meanwhile, the frequency of internet searches for relevant keywords may indicate interest levels for how consumers react to the online media. Additionally, although our data of media coverage density in each time interval between 2 consecutive mass shooting incidents was supposedly primarily derived from the reports in response to mass shootings that met Mother Jones' narrow criteria, for example, 1 perpetrator and at least 4 victims, some reports might actually discuss other mass shooting events with lower levels of fatalities, for example, broad definition of mass shootings. Such a mismatch due to the mix of media attention towards both narrow definition mass shootings and broad definition mass shootings might be jointly considered as media attention associated with the time interval between 2 narrow definition mass shootings. Therefore, our data actually suggests that increasing media attention towards various types of mass shootings jointly correlate with increasing incident rates of mass shootings. Recent evidence suggests a contagion in mass shootings, which refers to the phenomena that a mass shooting may temporarily increase the probability of a similar event in the immediate future. The contagion phenomena has been well documented in other forms of violent behaviors, including suicides and homicides. The relationship between media and violent behaviors has been documented by several prior studies. For example, Cantora and colleagues have reported a series of mass homicides occurring in Australia, New Zealand, and the United Kingdom, 1987 through 1999, in the context of possible media influences. Similarly, Phillips and colleagues have raised the concerns that homicides seem to have been rewarded by media attention. Kostinsky and colleagues reported that the clustering of threats of school violence following the Columbine massacre was initiated by imitation. Although an earlier study did not find the clustering of rampage murderers when they examined the data from 1988 through 1999, recent evidence did suggest this phenomenon when more data were extracted. Taken together, these lines of evidence have shown the influence of media on clustering or contagion of mass shootings. However, caution needs to be exercised when we attempt to infer the impact of media coverage. In other words, we might at best infer the greater media coverage might predict an earlier onset of the next shooting incident, but we would not clarify whether the increased incidence could be attributable to increased media coverage. To further examine if some specific shootings that receive unusually high media attention are outliers that bias the observation, we have also examined the post-event effects for 3 specific incidents. The mass shooting at Sandy Hook Elementary School in December of 2012, the mass shooting at Las Vanguard Strip October of 2017, and the mass shooting at Marjory Stoneman Douglas High School in February of 2018. The first case triggered the presidential initiative of firearm regulation reform proposals. The second case caused the largest number of fatalities associated with a mass shooting in the history of the United States, of the USA. The third triggered the largest nationwide protest that called for firearm regulation reforms. We found that the media index values, such as the number of daily online articles and online search interest level, were increased variably. Sandy Hook Elementary School shooting, 3%. Las Vanguard Strip shooting, 14%. And Marjory Stoneman Douglas High School shooting, 241%. The second case caused increased media attention, and the interval between this case and its following shooting incident was 17 days, which was a 0.7 standard deviation below the average or the mean distribution of the log transformed intervals. The third case apparently caused unusually heightened media attention, and the interval between the third case and its following shooting incident was 23 days, which was half a standard deviation below the mean of the distribution of the log transformed intervals. Therefore, these particular observations seem to follow the trend that media attention was inversely correlated with the interval between the current shooting event and the next shooting event, especially for more recent cases. Furthermore, we removed these outliers and reran the analysis. The results still show that higher internet media exposure was significantly correlated with a shorter interval between corresponding shooting and the following shooting. Therefore, the original observations were not biased by outliers that triggered unusually high media attention levels. Another limitation lies in the assumptions in the process of statistical modeling. For example, we relied on the cross-sectional data to evaluate ownership rates, wherein a spatial correlation structure is needed with priors specified from a Bayesian analysis. Our statistical approaches were hence different from Wallace's method in a recent study, and hence we did not replicate the prior findings that gun ownership could account for the incidence of mass shootings. Furthermore, we assumed shooting events were identified of each other in the Poisson regression model, while a linear time trend could exist. The concern might have been addressed by the validation of a significant effect of a second-order term. Finally, our assessment of future mass shooting risk was based on a narrow definition which might result in conservative estimates of the incidence rates and lead to biased effect sizes or risk factors. Similarly, inconsistent findings from the literature may, at least in part, arise from different definitions or classifications of predictors. Future research is needed to explore methodological challenges arising from the aforementioned issues in order to properly evaluate the time trend of mass shootings. That is the article, What Have We Learned from the Time Trend of Mass Shootings in the United States by PLOS ONE, published October 18, 2018, all by authors Ping Lin and Lin Fei, Drew Barsman, M. Hossein. Thank you again for your time.